Not the next method, overlap and save method. In this method, n2 minus 1 values computed incorrectly. That's a disaster. Okay? So, in this method, n2 minus 1 values computed incorrectly are discarded, and n2 minus 1 samples of the last part of each input segment is saved. The idea of the method, overlap and save, is saved and prepended to the next fragment or section or segment. Okay. X of n is divided into the sequences of length n1. This time no zero padding at the end of input signal, without any zero padding, okay? But the length of h of n is equal to n2 and n1 minus n2 zeros. Please be careful. n1 minus n2 zeros are added to its end. Okay. As a result, both the lengths of x of n and h of n will be equal to n1, the length of the segment related to the input. Okay. If we consider the convolution of these two, since n2 minus 1 zeros are missing at the end of the sequences, n2 minus 1 samples will have a wrong answer and should be ignored. Okay. If x of n pieces are arranged so that n2 minus 1 final samples of each piece overlap with the first n2 minus 1 samples of the next segment, and then n2 minus 1 first samples be ignored because they are wrong, then the correct answer will be obtained. Okay. Now, a very important illustration of the idea. Find the convolution of x of n with h of n using overlap and save method. Let n1 be equal to 6 and n2 again 3. X of n has been chosen as x0, 1, 2, 3 up to 13, with h of n being equal to h0, h1, h2. Now the solution. For the first segment where x of n has a periodic form of, this time please be careful, x0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. No zero inserted here. Okay? Compare this chunk with the previous one. We will have x0, x1, x2, x3, x4, x5. Right? Now, y of 0, of course, it's wrong. Okay? Will be x minus 2 h2 plus x minus 1 times h1 inside brackets, because it's wrong, plus x0 h0. Of course, x minus 2 this time will be x4 h2 plus x5 h1 plus x0 h0. x0 h0. Again, y of 1 not correct will be x minus 1 times h2 inside bracket plus x0 h1 x1 h0, or x minus 1 is equal to x5 times h2 plus x0 h1 plus x1 times H0. There is no way to correct these two samples. Of course, you have understood that the number of the samples being under question is equal to the length of impulse response minus 1. The length of H is 3, so you will have 2 samples under question. The same story for the previous one, but the previous one you were able to correct it. But for overlap and save method, there is no solution. Okay? Now, y of 2 is okay. Needs x0 times h2, x1 h1, x2 h0. Everything okay. y3, again, you see here how the index is increased for input. Okay? And the same story here. y5 will be okay for this method. y4 okay. Now segment 2. I need to go back to show the segment. The first segment was, please write it down, x0, x1, x2, x3, x4, x5. Now the next chunk should be x starting from x6, but we need to save these two samples from input stream for next stage. Okay, to provide the space for wrong answers in the next chunk. Okay, that's the tricky way. So we need to save. That's the name of the method. We need to save 2 samples from the input sequence for the next operation. So you see here, x4, x5 has again appeared, and the rest, x6, x7, x8, x9, from 6 to 9 new samples. Right. Again, y4 will be wrong, y5 will be wrong. Here you see the details. We will ignore it because we have computed y4, y5 correctly in the previous section. So we don't need this y4 and y5 for segment 2. Okay? Just ignore these two. y6, a healthy answer. y7, y8, y9. You see here how the data has appeared. Okay. Now, the third segment, again, x8, x9 preserved, but new samples are x10, x11, x12, x13. Again, y8, y9 will be discarded because they have already calculated. Now, y10, 11, 12, 13, the exact definition, you see all of them. Note that with this method, y0, y1, y14, and y15 cannot be calculated. Okay. The following program in Python is about the overlap and save method. Okay, we run the program. Now you see the results. X of n is a data string from 1 up to 14. H of n minus 1, minus 2, minus 3. Y linear will be minus 1, minus 4, minus 10, up to minus 76, minus 67, minus 42. Right. And the result for overlap and save will be minus 28, minus 22. Okay. the wrong results, and -10. Please consider the correct results -1, -4. Instead, we'll have -28 wrong, -22 wrong, but from -10, everything has been sorted out up to n. Now, the wrong samples at locations 0 and 1 with values -28, -22 has been reported. Difference between the results of linear convolution and overlap and save method is 0 for the correct interval starting from the sample -10 up to, you see here, -67, -42. Here you need to track it. Here you'll find it. Okay? 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 Now going back to lecture note, the same syntax. Just scrolling very fast. Now, the next topic. Autocorrelation of the sum of two signals. If the sequence y of n is the sum of two signals, x1 plus x2, then r double y of j will be defined. We are similar, the same topic. It will be equal to r double 1 of j, meaning that autocorrelation of the first signal, plus r double 2 of j, plus r1 2 of j, plus r2 1 of j. Okay? If x1 and x2 are uncorrelated, then their cross correlation is equal to 0. Expected value of r1 2 will be 0, and the same for expected value of r2 1. We are going to take expected value from left side and from right side. This is often the case, especially when one of them is noise, such as unwanted signals coupled to sensors, noise added by electronic circuits, quantization error, etc. In this case, expected value of r double y will be equal to expected value of r double 1 of j plus expected value of r double 2 of j. You may omit j to simplify the discussion. Moreover, if x2 is a white noise source, the samples are uncorrelated in white noise, we know, then for j not equal to 0, we have expected value of r double 2 of j being equal to 0. It means the noise samples are even uncorrelated to each other for a lag of greater than 0. That's the fact. Therefore, r double y of j can be used as an estimate for autocorrelation function of a noisy waveform. Okay? In other words, ACF of a sequence can be used to estimate the ACF of a signal when it is corrupted by cumulative white noise. And that's a great idea. The quality of the estimation when we calculate the ACF for a particular sequence improves as the number of samples increases. Okay, now applications. Correlation is often used to estimate the delay parameters of random or noisy signals. Another application is in matched filters, which are used in the radar's signal processing section. Now, estimating the period of a signal. From the existing relationship for ACF, we understand that ACF will be periodic with the same period. Okay? Therefore, the ACF of a signal can be calculated and then the cycle time can be estimated from the ACF. You can find it easily, the period, very easily computed. Now, the period can be accurately computed by considering the ACF peaks, which occurs at lags of 0 and multiples of period. Another method is to compute the DFT and find its peaks. The same results, but this time in frequency domain. Right. Delay estimation. Many systems, including radar and sonar, work by measuring the delay between a transmitted signal and its echo. This echo is often weaker than the transmitted signal and is corrupted by white noise that is uncorrelated with the original signal. If we calculate the cross correlation between the transmitted and received signals, we expect to obtain a maximum for the real delay. So, the use of cross correlation allows us to obtain the denoising effect at the same time as estimating the ACF of a signal corrupted with noise. We can get the best results from such systems by sending a signal whose autocorrelation has very strong peaks. So you are familiar with the name of such a signal. It is an impulse, but there are other types of signals that have similar property, such as pseudo-noise sequences. Right. Now, important conclusion. A periodic signal buried in noise can be estimated as the first one. Obtain the autocorrelation of the waveform to find the period of the signal, which you cannot see and observe it in normal situations because the signal has been buried inside a very strong noise. Otherwise, you could estimate and find it. But this time you need ACF, autocorrelation. Find the cross correlation between the noise contaminated waveform and an impulse train with the same periodicity.